Good morning, students. Welcome back to this algorithm class again. In the last few classes, we are discussing about various example problems solved using the divide and conquer method. In the last class, we saw one example for divide and conquer method, selection sort. Before that, we saw one example, quick sort, and both the algorithms, both the examples used one partition function. In the quick sort, values less than the partition value are pushed in front of it, values greater than the partition value are pushed back of it, so that the partition value will be placed at the right location of the final sorted sequence. Okay, then values before the partition value are again divided, and another partition value is used like this. We saw one example. The example was partial only. Now we see a full complete example for quick sort to sort the given list of random numbers. Okay, again I reiterate the idea. Starting from the left, you take the first element as the partition value. Well, the pivot value is compared with first values from the left side. Once a value greater than the pivot value is found out, you stop there. Then start comparing the pivot value from the right side elements. Once you come across a value that is less than the pivot value, there you stop it. Then you exchange the left side element and the right side element. That's how we will do it. Okay. Then the partition value will be placed at the right location. So with that understanding, you look at this example. You are given some 13 values. 13 values. The values given are 38, 8, 16, 6, 79, 57, 24, 56, 2, 58, 4, 70, 45. So for my convenience, I take the first value 38 as my pivot value. So what I will do is, I will compare the pivot value from the left side elements once. Okay. Then I will compare this pivot value 38 with the right side values coming from. So to move from left side, I use one variable called I. To move from right side to the left side, I will use a variable called J. Then once a value that is given greater than the partition value is found out, there I stop it. So with that understanding, you see here, I'm starting from the left side. 38 is compared with 8. 8 is less than 38. So I is moving from here to here. Okay. Then 16 is less than 38. So I moves from here to here. 6 is less than 38. Increment I. 79. Does 79 less than 38? No. 79 is bigger than 38. There you stop. I gets stopped. Okay. Then I compare the 38 from the right side. Does 45 greater than less than 38? No. Does 70 less than 38? No. Does 4 less than 38? Yes. J, there I stop J. Okay. So now currently J is pointing 4, I is pointing 79. So these two should be swapped. So 4 will come here, 79 will go here. So swaps 4 from here to here. So 4 comes here, 79 moves from here to here, 79 comes here. Okay. Again, the loop starts. Then 38 is compared with the next value, 57. Yes, 57 is bigger than 38. So you stop the value of I here. You stop I here. Then you go to the right side. Okay. Now you see 58, 58J. 58 is bigger than 38. So j is further decremented. Now you see here 2 is less than 38. So you stop j there. You stop j there. So j is pointing the value 2, I is pointing the value 57. You swap this value and this value. So 2 comes here, 57 comes here, 57 comes here. Okay. Then next iteration, you compare 38 with the next value. I is increment, I becomes this value. Does 24 bigger than 38? No. I is incremented. I comes here. Does 56 greater than 38? Yes. So you stop I here. Then you go to the right side. Currently my j is pointing this area. Now decrement j. Does 56 less than 38? No. Okay. You go to the next value. Does 24 less than 38? Yes. So j stops here. So j will stop when the value it is pointing is less than the pivot value. I will stop when the value it is pointing is greater than the pivot value. So here 24 is less than 38. So you stop j, and the final loop gets terminated when I is equal to j or I becomes greater than j. I is equal to j or I becomes greater than j. Now what is the value of I? I is available in the index j8. J is available in the index 7. I becomes greater than j or equal to j. So here I is greater than j. Greater than j. So there you stop this comparison mechanism. Then you swap pivot value with the value available in the j. J is pointing. J is having the value. J is having the value 24. So you swap. You interchange the 24 with 38. So this 38 is coming here, and this 24 is going there. 24 is going there. Now you look at the values before this 38, pivot value 38, 2, 4, 6, 16, 8, 24, all are less than 38. And you look at the values to the right side of 38, 56, 57, 58, 79, 70, 45, they are all bigger than 38. Now you see the 38 is placed in the right final sorted sequence. The problem is not yet over. So what you did for the entire problem, you should do it for the values before in front of 38. In front of 38. That's what we are going to do it now. So you bother only about these values now. You bother only about these values now. Okay. As usual, I take 24 is my pivot value. 24 is my pivot value. Then I increment I from this side, I decrement j from here. So currently my j is pointing, currently my j is here, my I is here. Now, does 24 is compared with 8? Yes, 8 is less than 24. Then I is moved. 16 is less than 24. Yes, I is moved. 6 is less than 24. I is moved. Then 4. 4 is less than 24. I is moved. Okay. Then 2 is less than 24. I is moved. No more elements are there. So there I stops. Okay. Then j is moving from right to the left. Now does 2 is greater than 24? Does 2 is greater than 24? No. So the j will stop once it comes to a value that is less than the pivot value. 2 is less than the pivot value, so j stops there itself. Now I is equal to j. So the interchanging will happen either when I becomes greater than j or I becomes equal to j. So I is equal to j. So the value available in the jth location and the pivot value will be exchanged. So this 24 will come here and this 2 will go here. That's what happening here. You see, this 2 is moved to this place and this 24 is moved to this place. Now you see the values in front of 24, they are all less than 24 and there is no value behind this 24 and 24 is in the right location. So from the given values, we have placed 24 and 38 in their right location of the final sorted sequence. Now we have to repeat the problem for those values that are in front of this 24. Yes, as our convenience, I take this 2 is my pivot value. So 2 is compared with the remaining values from the left to right, then from right to left. So I is here. Does 8 is greater than 2? Yes. So I stops there. I stops there. Then you start from right side. Does 4 is less than 2? No. Does 6 is less than 2? No. Does 16 is less than 2? No. Does 8 is less than 2? No. Further you go down. So j comes here. Now I value of I is greater than j. So the value of j and the pivot value are stopped. J is pointing the pivot value to. The pivot value is also 2. So when they are swapped, nothing gets changed. They are left as it is. They are left as it is. So now we have put 3 values of the given numbers 2, 24, 38 in their right location. We have to consider the remaining values, these values only we have to consider. So from these values, I take the pivot value, 8 as the pivot value. So 8 is compared with the remaining values from the left to right and the right to left. So when it is compared from left to right, does 16 is less than 8? No. You move further. Does 6 less than 8? Yes. So there you stop. There you okay. So 16 is greater than 8. There you stop I. Then you start from the right side. Does 4 is less than 8? Does 4 is less than 8? Yes. So there you stop. Okay. Here pivot value. Okay, so I stops here, J stops here. So you have to swap this I and J. So 4 is coming here, 16 is coming here, 16 is coming here. Then after swapping, you do the process again. Then 8 is compared with 6. Does 6 greater than 8? No. So you move further. Does 4 greater than 8? No. No more elements to go. So I stops there. Then J starts from here. J. Okay. Now when J stops from here, does 6 less than 8? Yes. So J stops there. J stops there. Now the value, now you see here, the value of I is, the index value of I is bigger than J. So the comparison stops there. You swap the value available for J with the pivot value. The pivot value is 8. the value available in the jth index is 6. So this 6 and 8 are swapped. 8 comes here, 6 goes here. Okay, so now we have arranged 4 values in the right locations: 2, 8, 24 and 38. They are all placed in their right location. So we have to bother about only these values only now. So as our convenience, I take this is my pivot value. Okay, 6 is my pivot value. 6 is compared with yes, 4 is less than 6. So there you stop I. Then J decremented. J is equal to 6 is equal to 6. So there you stop. I is greater than J. So there you stop. Exchange uh, the pivot value is 4. When you exchange these two values, so it becomes 4 comes here, 6 comes here, and 6 is placed in the right location. Then you are left with only one value. This is 4, and since it is the only 4, no more recursive, no more partitioning, and this element 2, 4 is also gets sorted. Now we have sorted for all the values to the in the front, in the first half of the given original problem. So they are the sorted sequence are 2, 4, 6, 8, 16, 24. That's how they are all sorted. Okay, 38. So the front half of the problem given numbers are sorted. Now we have to go for the remaining half. The remaining half is 56, 57, 58, 79, 70, 45. As usual, we take this element as the partition value. Okay, so the pivot value is 56. Okay, that is compared with the remaining values. Okay, here you see when you move from here, 57 is less than 56, there you stop I. Then you compare here. Okay, here you see 45, 45 is less than 56. So there you stop J. You swap this 45 with 57. So 45 comes here, 57 goes here. Then I is moved to the right side. Okay, when you move further, you see that 58 is in the 58 is bigger than 56. There you stop. Then you come down here 70. 70 is bigger than 56. You come down, you decrement J. 79 is bigger than 56. You come down still. 58 is bigger than 56. You come down still. Then 57. So yeah, 58. Then so here it is 45. Now this 45 J is here. Okay, J is in having the value of 45. My pivot value is 56. You swap the value in the jth index with the pivot value. The value in the jth index is 45. The pivot value is 56. When you swap them, 56 comes here, 45 comes here. So for the pivot, the pivot value 56 is placed in the right location, and as well as this 45 is also placed in the right location because this is the only element. Okay, then you go to the elements behind of this pivot value 56. From them you consider one pivot value 58. Okay, when you do that, 58 is my pivot value. It is compared with the 79. Yes, 79 is bigger than 58. There you stop. You start here. 57. 57 is less than 58. There you stop. So you exchange this 57 with the 79. So 57 comes here. 79 comes here. Then you go next. You consider next location. You see that 70 is bigger than 58. There you stop. Then you come down. You see here. Here you see 70 is bigger than 58. So you come down further. 57 is less than 58. So J stops there. Okay, you swap the value in the jth index with the pivot value. The value in the jth index is 57. The pivot value is 58. They are all exchanged. So pivot value 58 is placed in the right location. When you see that the next value 57 is also placed in the right location. So we have to consider only these two values now. Okay, this is my pivot value. We compare this. 79 is bigger than 70. There you stop. You then J will come here. So 70 is less than 70 is less than the pivot value 70 equal. So you swap them 70 and with 70. So what happens? 70 is placed in the right location. Then you are left with only location, and that is the pivot value, and that is the jth value that is also swapped. So 79 is also placed in the right location. You see that 56, the values in the right side, they are also sorted. 45, 56, 57, 58, 70, 79. Ultimately, you see that the entire elements 2, 4, 6, 8, 16, 24, 38, 45, 56, 57, 58, 70, 79, they are all sorted. That is the beauty of this quicksort algorithm. Here we have seen one complete example of quicksort. Okay. You can write your own illustrative problem and sort it using this quicksort method. Based on this example, you will find that this quicksort works very clearly. Very clearly. Okay. Later we have seen one selection sort also. Just to recall what we have discussed about selection sort, there also we use this partition function. There we try to find some kth smallest value. When we try to find some kth smallest value, instead of finding the kth smallest value, we find some jth smallest value. Okay, so if both j and k are same, then we have found out the correct smallest value. Otherwise, if the jth smallest value that we have found is less than the kth smallest value that we are desiring, then my kth if my j is less than the k, then my kth smallest value will be available somewhere in the range is j plus 1 to n. Otherwise, if my k is less than j, then my kth smallest value will be available from a of 1 to a of j minus 1 that we have seen. So this we will keep on doing until kth smallest value is found out. Then by then you would have sorted some of the numbers. Then you try to find some other smallest number. There also you will arrange some more numbers in the sorted sequence. When you keep on doing that, ultimately the entire numbers will get sorted. That was the idea behind the selection sort that we have discussed in the last class. In today's class, we have seen one complete example of quicksort. In tomorrow's class, we are going to discuss about one beautiful technique to multiply two square matrices. Whose dimensions are in the order of 2 power k. That is square matrices of dimension 2 by 2, 4 by 4, 8 by 8, 16 by 16, like this. Such matrices, how to multiply. You will find that the conventional way of matrix multiplication will take more number of addition and multiplication operations than the divide and conquer method. Simply saying, the divide and conquer method of matrix multiplication will reduce the number of operations used to multiply two matrices. So the technique is called Strassen's matrix multiplication that uses the divide and conquer method. The Strassen's matrix involves quite a few number of formulas. When you apply those things, you will find that the divide and conquer method matrix multiplication will use lesser number of operations than the conventional matrix multiplication methods that we will see in the coming class, next class. Okay.